Hey guys, welcome back. Well, it's Galaxy season, which means it's long focal length season, which means it's off-axis guider season. So I wanted to share with you a couple of procedures I go through when I'm planning an imaging session and setting up my off-axis guider, and one way to use Stellarium markers to ensure that a very bright star is in the middle of the field of view of your off-axis guider to help you in focusing your off-axis guider. Let's get started. This is a view of PhD2 during a recent imaging session. Things were not going well for a couple of reasons. First of all, if you look at the guiding graph, it's absolute trash. And the reason is because we were having quite a bit of wind. So I finally just had to shut the imaging session down for the night and call it quits. And I haven't been out since because of the weather. Another thing that was going on, it's very difficult to find a guide star. I have a exposure setting of 6 seconds, and it's all I can do to pull out a very faint star here. Now, what you're seeing here, this bright spot in the middle of the sensor down at the bottom, well, that's what I showed a couple of videos ago when I took this contour plot, made this contour plot of the light coming up through the sensor. So what you're seeing here is PhD2 trying to amp up automatically the gain so that it can finally see a guide star to work with. And as a result, it's blowing out this area of the sensor where there are no good guide stars to start off with. And now that area is just exceptionally bright. So what I'm going to show you is a little procedure. It takes about 20 minutes in the pre-planning stage and can be done during the day. And that will help us to avoid wasting hours, if not entire imaging nights. This is kind of a cross section through my off-axis guider. What you're seeing here is the gold part. It's kind of the prism. The stalk goes up into the off-axis guider assembly here that holds the camera. This is the imaging sensor. This rectangle here is the imaging sensor as it's projected down onto the prism. I'm using an ASI 174, so it's a 7.1 millimeters by 11.3 millimeters in size, which is smaller than the Celestron prism that I have, which is 12.5 by 12.5 millimeters. What we have to do is enter some critical geometry parameters into the Stellarium Oculars plugin so that we can actually see what the off-axis guider will see. What I have is a section set up with the imaging camera parameters here. I'm using the ASI 294MC, so I've got the number of pixels in the X direction, the larger number, the smaller number of pixels in the Y direction, the corresponding lengths of 19.1 and 13 millimeters. And then there's a rotation angle. We're going to talk about the rotation angle in just a little bit, but let's just consider that to be 0 for now. In order to set up the off-axis guider, you've got to come down here and tick in this little area here. That will activate these boxes here for data entry. And one of the parameters that always seems to confuse a lot of people is this prism/CCD distance. And what this actually is a distance from the center of the off-axis guider body, so down along this line here, up to the bottom of the prism or the CCD. In my case, the sensor is smaller than the prism, so I want the distance from the center of the off-axis guider body up to the bottom of the sensor. Take a pair of calipers and measure from the inside radius of this body up to the bottom of the prism. And then I measure the inner diameter of the off-axis guider body. And then with a little bit of simple math here, take that 47 millimeters from the bottom of the off-axis guider body up to the prism, subtract off the radius of the inner radius of the off-axis guider, which is just 73 over 2, add on the distance to halfway up the prism height, which is the 12.5 divided by 2, and then come back down by half the height of the sensor, which is 7.1. And so take all those numbers together, and that leaves me with 13.2 millimeters, and that's what I enter into this area here. The boxes below are the guide sensor height, which is 7.1, and the guide sensor width, which is 11.3 millimeters. And once again, we'll leave the rotation angle or position angle of the off-axis guider 0 for now. Now, something that I also do is to define a bullseye, in other words, the center of the chip here. Stellarium doesn't give us a little crosshairs in the middle of our off-axis guider view. So if you want to know where the precise center of the guide camera field of view is, imagine a 1 millimeter by 1 millimeter sensor. That little box would be right there in the center. And so now I'm going to take all of this information and copy it over to another sensor. So I'll have the same information for the camera, but in here, instead of using 13.2, I'm going to put in the numbers corresponding to a hypothetical 1 millimeter by 1 millimeter sensor. And that means I'm not subtracting off here by 7.1 divided by 2. I'm subtracting off by 1 millimeter divided by 2. and that leaves me to 16.25 that I put in here. And then for the sensor height and width, I put in 1 millimeter in each of those slots. And I named this particular combination the ASI 294 with bullseye. And then finally, when we're in Stellarium, you might want to go ahead and set the magnitude of the stars that are shown by Stellarium to be around 11.5 or 11 or brighter. Okay, so now let's talk about the camera rotation angle and the off-axis guider position angle. Right now, we're going to start off with them at default values of 0. Let's go over to Stellarium. We can come over to the configuration window, select that, go into plugins, and then just scroll down here and you'll find Oculars. Now, in your case, if you don't have it set up, then this isn't ticked. You have to tick this and then close this down, close out of Stellarium, load Stellarium back up, and then you can go in and add and mess with the configuration parameters in here. I also have it checked here to have an on-screen control panel, which is this control panel up here in the upper right-hand corner. Let's just close that down. Let's close this down. Now, one of the changes we want to make when we're doing this framing study is to make sure that Stellarium isn't tracking stars. And so let's go down here and pause Stellarium so it freezes the image. Then let's go over to the clock and turn it to a time that represents the dark time here. So I'm just going to set that to 2100. And so now it's dark. And now we can go over to the target that I have in mind, which is the Leo triplet. And now you can see I have already placed a marker here. We're going to talk about these markers in a minute. Now we can activate the ocular setting, and you can see we have our imaging camera and we have our off-axis guider. What we want to do is shut this down and then just play with the angles here until we get the Leo triplet to fit within our field of view. And this is the center of the field of view, this marker. So let's go ahead and go over to the rotation angle for the camera and just click this around until I can get the galaxies comfortably within this field of view. And 60 does a pretty good job. We can keep going. There'll be other options here. And we get to 240, and then that is a good combination right there. So we'll just leave it at 240 degrees. And now it's time to take a look at what guide stars we might have available. And this actually looks pretty promising. At a 0 angle here for the position angle of the prism, I've got a pretty good bright guide star right here. We have to keep in mind that we're going to be imaging most likely on both sides of the meridian. When we go to the other side of the meridian, this view is going to flop 180 degrees. So let's do that. Let's go 180 degrees out of phase and see what we end up with. And now you can see we only have one guide star here, potentially bright enough for us to guide on. What I'd like to do is capture and have available a few more guide stars. So what if I came over here and I changed this by maybe plus 10 degrees? And now if we go back over to the east side of the meridian, you can see that when this gets to 240 right there, now we still have that star potentially available, but we have some other stars here. So we're still in pretty good shape. And you can see with this particular target, there are whole regions here where you have no stars in this angular zone here. So it's not a trivial task with some targets finding guide stars to work with that are bright enough that you'd want to use them as guide stars. We've done our little framing exercise and we come up with a rotation angle for the camera of 240 degrees and a position angle of 10 degrees for the off-axis guider. Now we've got to take these angles and place our imaging camera and our off-axis guider so that we're reproducing these angles. Take your telescope and set it on the dovetail bar on a flat level table. Let's work through this in a systematic way. For example, if we start with a 0 angle for the rotation angle of the camera and a 0 angle for the off-axis guider, this is what that would look like. The ZWO camo would be rotated so that the writing was on the left side going vertical like this, and the off-axis guider would be going off to the right. And so it's going to be a very simple two-step process. Again, this is something we don't do physically. You're not touching the camera at this stage. You're just mentally going through this exercise, and then that will leave us with the orientation that we're looking for. And only then will we actually touch the camera and set the angles so that they properly match what we just did in Stellarium. We're going to start by rotating the camera and the OAG together to get to the 240. And in the second step, we just rotate the off-axis guider by the 10 degrees that we want to get to here. We have a positive 240 degrees, which means we're going to rotate this setup clockwise. And so if I go from a 0 angle here to 60, that's what it looks like. You notice that the off-axis guider is moving with the camera. There's 120, there's 180, and there's 240. So now it's time to do the second step because we've satisfied the 240. In this case, we're only going to rotate the off-axis guider, and it's a positive angle, and that means we're moving in the clockwise direction, but we're moving the off-axis guider relative to the camera. So we're leaving the camera where it is, and we just rotate the off-axis guider. And there's our 10 degrees. And so now it's just a matter of taking this picture, this orientation, and setting our camera and off-axis guider up so it looks like this on the back of our telescope, which is sitting on that table. So here's my actual setup, and you can see here's the writing for the camera. It's the writing of the camera here. If you do the math, that turns out to be that's about a 30-degree angle. We have the off-axis guider. You can see it's not here. It's rotated over a little bit, so that's why it's off. And so this image here is what I've replicated on the back of my telescope. Now, how do we do that? What we're going to do is start off by recognizing that the angle up here of this surface is not the 30 degrees here, it's rotated 10 degrees back. So if I take a digital angle gauge, I measure the top flat surface of that off-axis guider up here to be 20 degrees and then lock it down with the set screws so it doesn't move. Now I can unlock the set screws that hold the camera, and I can rotate the camera without disturbing the angle that the off-axis guider is set at. And because I've got some USB ports here, I can put in a USB drive here that has a flat surface and just use that to set my digital angle gauge on, and I should measure the 30 degrees that I have for the writing across here on the bottom of the camera. So now these angles match what we found in Stellarium. So let's go back over to Stellarium and use the markers feature within Stellarium to get that bright star in the field of view of the off-axis guider. It turns out that Dubhe is up and is in close proximity to our target here. So I'm going to go ahead and scroll out and select Dubhe. There it is. We're still on the east side of the meridian. And now we have Dubhe in the center of the field of view of our imaging camera, but that's not what we want. We want Dubhe to be in the center of our off-axis guider view. Now, for example, I could just simply bring it in here. The problem is Stellarium doesn't give me a crosshairs or a bullseye for the off-axis guider view like it does for the imaging sensor. So this is why I suggested we go ahead and create that separate off-axis guider setup with a bullseye. And now all I have to do is come over here and select it. Now, when I want to position Dubhe in the center of the ASI 174 field of view, then all I have to do is do this. I can come in and just set it in that little box, move the cursor over to the center of the imaging camera, press the Shift key and the left mouse button, and that will assign a marker to that location in the sky. If I want to delete this marker, then all I have to do is get close to the marker and press Shift and the right mouse button, and that will delete the marker. But for me, I'm going to go ahead and put it here. This is where our imaging camera should be pointed in order to put Dubhe in the center of the field of view of our off-axis guider. Now, just to be on the safe side, let's go ahead and set this up for the other side of the meridian as well and put another marker in place just in case that's what you're going to be working with. All I have to do is rotate this whole image by 180 degrees. And now we can bring Dubhe into the field of view, the center of the field of view on this side of the meridian, and set another marker with Shift, left mouse button, and there we have it. Now, let's say we go back to marker 3, and let's go back to our full imaging sensor, and as you can see, we have Dubhe nicely in the center of the field of view of our off-axis guider. Now you want to go over to Nina, for example, and load in the coordinates of that area of the sky. You can see it says marker 3. It's going to now find that area of the sky and show our field of view, and Dubhe, of course, will be offset because we're going to be looking at, here's the field of view of our imaging sensor. Dubhe is up here. But remember, we're centering this in the field of view of our guide camera. And now all you have to do is do a slew and center here. And that would put your imaging camera right here in this nondescript area of space. But what you would have is Dubhe in the center of the field of view of your guide camera. Once we take a picture with our imaging camera, whatever it happens to be here, it's obviously the Leo triplet. I can take this image and do a plate solve, PixInsight, for example, and find that the angle PixInsight tells me that it has is 120.8 degrees. Now, it turns out that the angles that are being used by PixInsight are about 360 off from those that are in Stellarium. For example, if I take 360 degrees, subtract off the 240 that we set from Stellarium, we would have 120 degrees. And what this is saying is that instead of having 240 degrees, it looks like I'm actually within a degree, but closer to 239 degrees in Stellarium rather than the 240. Now that we've confirmed our camera orientation, we can go back to the image that we see in our PhD2 screen when we have Dubhe in the center. And this is what I got when I tested this out. Here's the field of view of my ASI 174. Here's Dubhe. Let's just blow up this section of the field of view so that we can concentrate on what we're seeing here. You're going to have to mirror the pattern of stars you see in the PhD2 window about this vertical line, and then they'll match up with what you're seeing in Stellarium. This would be a good time to go out to the scope and move the camera in and out to see if you can find a rough focus. Once you get it to a proximate focus for the bright star, lock it down with the set screws and then use the helical focuser if you have one to dial in the focus. And because it's a bright star, you can go ahead and put a Bahtinov mask on your scope and use the Bahtinov diffraction spikes as a guide in setting the focus for your bright star. Depending on how meticulous you were in setting this up, Dubhe may be somewhere else in this field of view rather than close to the center as mine is here. But for example, let's just keep in mind that this sensor for the ASI 174 is 7.1 millimeters in height and 11.3 millimeters in width. And I put this box in here. This box represents plus and minus 1/2 arc minute, which is the pointing accuracy I set for Nina when it's doing the plate solving and trying to position the scope for a RA and deck coordinates. It looks like that Dubhe is outside of this box. If it were inside this box, then frankly, the error may not be in the setup of the off-axis guider. It just could be the pointing error of the telescope, and I wouldn't mess with it. Even as it is for this particular view, I might not change anything. But let's just say, for the sake of discussion, that you did want to change things, that you did want to update the parameters that you set up in Stellarium for your off-axis guider. The vertical distance for the star from where it is to the center of the prism is about 0.36 millimeters. Now, I'm getting that just using PowerPoint and saying, well, I've got a line here that's this long. I know this length here is 7.1 millimeters. So I'm just ratioing this distance here, and that tells me that I'm at 0.36 millimeters. And since the star is above the center of the field of view, and we used our bullseye setting to put Dubhe in the center of the field of view, what this means is that the 13.2 millimeters that I originally typed in for prism CCD distance in the Oculars setting tab is actually too large. I need to reduce that by 0.36 millimeters. Now, the other distance is a little more challenging. In this case, we have, again, by scaling, about 0.3 millimeters, measuring this distance in PowerPoint and knowing that this distance corresponds to 11.3 millimeters. I just ratio that back to 0.3. But what this distance comes from, it's either from rotation error in the camera, and I just pointed out a second ago that my camera was off by almost a degree. So that's one source of potential error. The second is that you have rotation or position angle error. This is the position angle error in degrees. This converts it to radians. Radian angle times the radius gives us the distance, which is 0.3. And in our case, the radius is equal to that 13.2 plus the 7.1 divided by 2, that's this distance here. So the 13.2 comes up from the center of our imaging sensor. 7.1 divided by 2 takes us up to the center of this image, but then I've got to subtract off the 0.36 error that I have. And so that leaves me with 16.4 millimeters. And once I plug 16.4 into here, I can solve for delta theta and find out that I have a rotation error of 1 degree. And again, as I said, that rotation error could be position error of my off-axis guider, or it could be position error of my imaging camera. Now, take these numbers and go back over to the off-axis guider's parameters, the ocular setting, and see if we can't change the parameters so that we're, in essence, replicating what we're seeing here. So here's our ocular settings again from Stellarium. Rotation angle, I found that I need to change this to 239 based on the plate solution that tells me what the rotation angle of the field of view actually is for the imaging camera. And here I need to come down by 0.36 millimeters to 12.8. based on the fact that that guide star that should have been in the center of the field of view was actually higher, actually above the center of the field of view, and therefore I need to subtract off that 0.36 millimeters. And then finally, there was a 1 degree angle variation of where Dubé was relative to the center. However, if I implement this change, then that fixes this error. So there's nothing in my case for me to change here. You'll have to look at your particular case to see if the error that you get in here solves this problem or if it just compounds this problem. Again, that's going to be at a case-by-case basis if you want to go down this path and improve the accuracy of your field of view for your off-axis guider. Stellarium is one of the most useful tools available for planning out imaging sessions. I know there are other planetarium software out there that do the same things, but I've been using Stellarium for a long time now. It's a really valuable tool for us astrophotographers. One of the things that's really nice about it, particularly if you're dealing with a long focal length system with an off-axis guider, is you can actually model the field of view of your off-axis guider so that you can plan out an imaging session knowing that you have a bright enough star available for guiding. We want as bright of a guide star as we can possibly get. And at long focal lengths, there aren't a whole lot to choose from. So that's why you kind of want a procedure that you can perform during the day and dial in the position of your off-axis guider using, for example, Stellarium to identify bright stars as guide stars in the area. So it's just one of those things you can do that is going to really simplify your life when you get outside in the dark and you will already know that you have a guide star available. The Stellarium markers feature is really useful. It really does give you an opportunity to properly frame a target and to identify the center of the image, those RA and DEC coordinates, and pass them to Nina so that the scope will go to that particular location. Stellarium markers are also useful in calibrating your off-axis guider. You can set a marker at a nondescript area in space such that a very bright star is in the center of the field of view of your off-axis guider, which is really useful for focusing the guide camera because now you can use the Bahtinov mask. Finally, if there's a significant error of the star being off from the center of the field of view, you can update the parameters in the Oculars setting in Stellarium to refine the position and correct for errors that might have crept into the process. Of course, none of this matters at all until you have a clear, no wind, no moon night. I mean, how long could that take? That's all for now. I'll just leave you with a view of what my nighttime sky looks like lately. See ya.